So good afternoon or good evening, depending where you are. Welcome to the last part of this workshop. Our first speaker this time will be Renato Diaz from Universidad Federal de Rio de Janeiro on conic bundles on rational elliptic surfaces. The floor is yours.
Okay, thank you very much. I'd like to thank the organizers for inviting me for this talk. And so I'm going to talk about conic bundles on rational elliptic surfaces. So we're going to start with a setup. First, K is going to be an algebraically closed field, unless I say something different about it. The characteristic is arbitrary, except from 2, and all surfaces are going to be smooth and projective over K. Okay, so I'm going to start with some definitions. What is an elliptic surface? Surface X is called elliptic if there is a curve C and a surjective morphism pi from X onto C. We call this map an elliptic fibration, and this map must have 3 properties. Almost every fiber is an elliptic curve. That's why the name elliptic fibration. We're going to assume that we have a section for this fibration. And we're going to ask for relative minimality, which is none of the fibers have an exceptional curve as a component. These are the 3 properties that we ask for. In this remark, if we have this section sigma, the image of this map is also called a section. So this image is a curve. So we may also call this curve a section. So here's a simple picture of a simple representation of an elliptic fibration. We have the map here from X to C. We have some fibers here. Some are singular, some are smooth. Anyway, this is just a representation. We also know all the possible singular fibers of an elliptic fibration. That's Kodaire's classification. You can see that some of the fibers are reducible, some are integral, some have multiplicity, so they are not reduced in this case when they have multiplicities. And yes, so I'm also going to talk about the generic fiber, which is important. We have taken elliptic fibration. We take the generic point on C, and the generic fiber is this, and this is an elliptic curve over KC. So it's an elliptic curve over the function field of C. So this is another representation here. Here's the generic point and the general fiber, the generic fiber here. Okay, so we also have the generic rank. I've just said that the generic fiber is an elliptic curve over KC, and by a Mordell-Weil theorem for function fields, we can say we have this decomposition. we have a free group here, which is ZR, and a torsion part of the group. And we call this R the generic rank of X. That's an important number for us. Okay. So I'm going to talk about rational elliptic surfaces, which is just an elliptic surface which is rational. It's just that. And I also remark that when pi is rational, when the vibration is rational, we must have that C is isomorphic to P1. That this always happens. Okay. So I also need to define a conic bundle. So let pi be a rational elliptic surface, and a conic bundle on X is a surjective morphism whose general fiber is a smooth irreducible curve of genus 0. So basically, conic bundle is a pencil of genus zero curves, basically. And what I'm trying to do is to find conic bundles on this rational elliptic surface. Okay. And by the way, phi may have singular fibers. The conic bundle may have single fibers, and we're going to talk about them in a second. Okay, so where do conic bundles show up? They actually show up in a lot of places because, like I said, the conic bundle is basically a pencil of genus 0 curves, so it can show up anywhere, right? But I'm going to talk about a few instances where we can find them, and they're important. So in the classification of minimal rational surfaces, this has been done by Skovsky in '79. He proved that if S is a minimal rational surface, then one of the following holds. S is either A2 or isomorphic to the quadric on P3. It can also be a Del-Pezzo surface, or it admits a conic bundle with certain singular fibers. I'm not going to talk about it here, but I'm going to talk about more general singular fibers. In another instance where conic bundles show up is in the minimal model program, in the classification of threefolds. This is also from Skovsky in 1987. If W is a threefold, then we have one of the following. W can be a K-funnel. It can admit morphism onto a curve whose general fibers are Del-Pezzo surfaces. So it's a sort of Del-Pezzo fibration or something. Or they admit a morphism onto a surface X whose general fiber is a smooth irreducible curve of genus 0. So that's like the conic bundle that I defined a moment ago, but this is in higher dimension. So these are two instances where this can show up. So why do I want to talk about conic bundles on rational elliptic surfaces? This was basically motivated by the works of Cecilia Salgado, which is my PhD advisor. And I'm going to talk about some of these works. So in 2012, we have this article on rank of fibers on rational elliptic surfaces. And more recently, rank jumps on elliptic surfaces and the Hilbert property. So here we have the hypotheses are that K is a number field, X is geometrically rational, which means X is rational over K bar, and pi is an elliptic fibration with the generic rank R. So the question is, if RT is the Morgenthau rank of some fiber, what can we say about the sets where the rank jumps? Sorry. So we are trying to compare the generic rank with the rank of a given fiber. So we want to see if this set where the rank jumps, we want to know what it looks like, and also where the rank jumps by 2. And they prove this theorem, which is if there is a genus 0 curve C over K with intersection 2 with the anti-canonical divisor, then the set where the rank jumps is not thin. Not thin, it's a very precise notion. I mean, when we say that the set is not thin, first of all, it means that it's an infinite set. So the rank jumps infinitely many times, which is very interesting. But not only that, not thin has to do with the Hilbert property for varieties, which is an important concept in arithmetic geometry. Moreover, if pi does not become constant after quadratic extension of K, then this set is also not thin. So that's a very interesting result. And so why am I mentioning this? Because the key ingredient in the proof of this theorem, I mean, there are a lot of ingredients, but one of them is that the linear system induced by C is actually a conic bundle. So this curve C deforms into a linear system, which is exactly a conic bundle. And moreover, for almost all D in this system, the elliptic fibration, we get a new elliptic fibration from this change of basis. And this new fibration has generic rank strictly greater than R. So that's where the rank jump occurs. So here we are with conic bundles. And I also had motivation from these 2 articles, also from Cecilia and from Alice Garbagnati, where they study K3 surfaces, elliptic fibrations on K3 surfaces. So the problem is you have a rational elliptic fibration and a degree 2 map, and this degree 2 map induces K3 surfaces, which is this one. So the point is they classified all the elliptic fibrations on this K3 surfaces. And the key ingredient here is that if phi is a conic bundle on X, when we compose it with this projection, this natural projection from the base change, we get a genus 1 fibration. And sorry. So we get a genus 1 fibration, which in many instances has a section, and this came from a conic bundle. So if we know conic bundles on X, we can possibly get new elliptic fibrations for the K3 surface. And there's also another article which was important for me by Michele Artebani, Alice Garbagnati, and Antonio Lafati about Cox rings on extremal rational elliptic surfaces. So the problem is here K is C, complex numbers, and we have a rational elliptic fibration with rank 0. I mean, extremal rational elliptic surfaces means the generic rank is 0. So in this case, the Cox ring, which is the algebra generated by these vector spaces, is a finitely generated algebra. So they're interested in determining a minimal set of generators for this Cox ring. And one of the conclusions that they arrive is that in many cases, every minimal set of generators of the Cox ring must contain an element G, where D is a fiber of a conic bundle. So this is also another example of conic bundles getting into the picture. So so these articles that I've mentioned, these articles that I've mentioned have very different, they talk about very different problems with very different approaches, but conic bundles are always an important part in this article. So that's why my advisor Cecilia recommended me to think about conic bundles and try to understand them better. So what were my goals in my work? First, I want to try to understand conic bundles on rational elliptic surfaces in greater detail. I mean, I'm going to explain that better. I'm going to be more precise, but that's basically what I'm trying to do, and try to work in arbitrary characteristic if possible. All the articles that I've quoted are in characteristic 0. So I'm trying to go further with arbitrary characteristic and build some concrete examples. So that's what these were my goals. And now I'm gonna talk about the results that I came up with. So here K is algebraically closed of arbitrary characteristic except from 2. So I've shown that conic bundles can be represented by certain classes in the Roncevari group. I'm going to talk about this result in a minute. I've also classified all possible fibers of a conic bundle on a rational elliptic surface. And I've also tried to understand how the fiber configuration of pi affects the possibilities for conic bundles on X. So this is what I've managed to do. So the first result is the numerical representation of conic bundles. So here's the theorem. If D is a Roncevari class such that D is an F divisor with self-intersection 0 and intersecting the anti-canonical divisor by 2, then the linear system induced by D is a base point free pencil, and the induced morphism is a conic bundle. So and a corollary of this is that the set of conic bundles on X is in bijective correspondence with these classes, with these Roncevari classes. So I need to remark that this was already realized by Garbinati and Salgado in their paper. So, but my contribution was to work through the details and generalize it for arbitrary characteristics, except from 2. So the second result is the classification of conic bundle fibers. So here, if we have a conic bundle phi, then and D is a singular, is a fiber of phi, then D must fit one of these types here. I mean, this is the intersection graph of the fibers. So type 1 is the general fiber, which is the smooth irreducible curve genus 0. Type 2, we have 2 exceptional curves intersecting at a point. Type 3, we have this sort of chain of curves, all of them with multiplicity 1. Type 4, we have a double exceptional curve here with a multiplicity 2. And type 5, which has this form. So the interesting thing is that we have a sort of converse here, which is if D is a divisor, an effective divisor, which fits any of these diagrams, then it induces a conic bundle with its linear system. So, and this has to do, of course, with this correspondence here in the corollary. So that's probably the most important result, this classification. And third, we have the relationship between fibers of pi and the fibers of the conic bundle. So here's the theorem. X admits a conic bundle with a type 2 fiber. If that happens, then pi has a positive genetic rank. It admits a type 3 fiber if and only if pi has a reducible fiber distinct from 2 star. It admits a conic bundle fiber type 4 if and only if it has at least 2 reducible fibers. And admits a conic bundle with type type 5 fiber if and only if pi has an unreduced fiber, or a fiber IN with n greater or equal than 4. So, and by the way, these last 3 items are if and only if, except for the first one. So I do have a conjecture that the converse is not true. I'm still working on it, but I think it's a nice problem. Which is just a second. Okay, I don't have much time, so I'm not going to talk about it too much. But my conjecture is that the converse in item A is not true if pi has a 3-star fiber. Okay, so now I'm going to show to you some concrete examples. I mean, this problem was a very geometric one, a very visual one. So it was, I have to work through a lot of pictures and diagrams. So I'm going to show some of them to you. So first of all, how do you construct rational elliptic fibrations? This is a standard method. Every elliptic fibration can be constructed this way, which is this. You take 2 cubics on P2. In this case, we have C and a triple line, 3L. And we get the linear system defined by them. So we have here 3 points, this one, and this one, which are the base points. They have multiplicity because this triple line has multiplicity. So we blow up the base points. Each of them must be blown up three times, and so we have 9 blow-ups in total, and we get this picture here, which is this is a 4-star fiber, and these colored curves here are the fibers of the elliptic fibration. So, and every rational elliptic surface can be constructed this way. So you can take any pencil of cubics you want and do this. So it's a very visual way of constructing them. So now I'm going to show how I constructed conic bundles. I take the pencil of cubics, which is these 2 cubics that I talked about earlier, and then I take a pencil of genus 0 curves. In this case, I've took the lines through this point in the middle. So this is a genus 0 fibration, a genus 0 pencil on P2. So we blow up the base points like we did before, and we get this. So the lines here are sent to these lines here. And this is the conic bundle. This is precisely the fibers of the conic bundle. So this is how you construct rational elliptic fibrations and also the conic bundles. There are more ways of constructing conic bundles, by the way. I took this pencil of lines, but you can take a pencil of conics or a pencil of singular cubics, which have genus 0. So there are many ways to construct this. So using this method, I've built many examples. This one, for example, we obtain a type 5 fiber, this fiber here in pink. Here we have a type 2 fiber, which is 2 exceptional curves meeting at a point. here we have Conic Bundle with type 2 and type 3 fibers, and so on. I mean, you can do examples like this forever. It's a very, we have many examples. Here we have many fibers of type 4, which is it's a kind of nice picture. And there's also another way of constructing conic bundles, which is by making combinations in the intersection graph of curves in X. Like I said in the theorem, we have this converse. If you have a divisor which fits any of these diagrams, you can obtain a conic bundle. So that's another way to obtain them. So you can, here we have a 4-star fiber and two sectional curves, which are sections P and P prime. So you can just take D as this chain here, and this defines a conic bundle. You can take two reducible fibers like 3-star and I2 and choose D as this guy, and we have to adjust the multiplicity of P because it has to be a double component, but that's no problem. You just adjust the multiplicities and you get a conic bundle. This is just another example. So I think my time is up. So thank you. Thank you very much.
So let's thank the speaker. And are there any questions?
I have one, Louis, if I can.
Sorry?
I have a question. The first
Okay.
method, in the first method for constructing conic bundles, your strategy is change the curve, the cubics, and then take pencils of conics or rational curves, and in this way you obtain the fibers. I mean, you want. This is your strategy, right?
Yes, exactly.
Right.
Yes, you take a pencil of genus 0 curves on P2, and you transport them to the elliptic surface. That's
and changing the curves, changing the cubics, you get different fibers, right? This is your, I mean, what you get. If you change the cubics and the pencil, you can get different fibers, right?
Yes, exactly.
Okay.
Exactly. Yes.
Okay. This was my question. Thank you.
Any more questions? Okay, so let's thank the speaker again.
Thank you very much.